In the last lecture, we talked about classical cryptography. We talked about Caesar ciphers, affine ciphers, substitution ciphers, right? And finally, at the end, we were talking about the one-time pad, which was actually shown to be secure and so on. Now we're going to move on to what's called modern cryptography. And one could say that maybe the one-time pad, together with its perfect security, is sort of the beginning of that, right? Now, the basic communication problem is still the same. So it's common to have a setting where you think of Alice wanting to communicate with Bob. So Alice is the sender, Bob is the receiver, and there's an eavesdropper, Eve, which is sort of spying on the communication channel. And so the way this works is that there's some plain text, M, that Alice wants to send to Bob. And here they share some secret key. So they share some secret key that Eve doesn't see, right? And then the idea is that this, having the plain text and the key, there's this encryption algorithm that depends on the key, that you are able to encrypt the message or the plain text with this key, and you get a ciphertext, and that's what you transmit through the channel. And the goal is that Bob, with the key, is able to decrypt this, but for Eve, it should be very hard to do so because she doesn't know the key, right? So the important point here is that the communication channel is public, and so we should assume that Eve sees whatever is sent. And so security does not come from hiding the method. So you're not hiding the encryption. The encryption is also public, like how it works. The key is private, but you're not, the function that you use is not assumed to be private. So we should assume Eve sees whatever is sent. Security does not come from hiding the method or hiding the channel. Security comes from the key. And so this is the basic setup for what's called symmetric key encryption, where Alice and Bob use the same secret key for encryption and decryption. That's why it's called symmetric, right? So let's recall the one-time pad. So how did that work? For a message M and a key K of the same length, the idea was that you did the encryption by adding the message to the key. Here I'm writing it as an XOR because we're thinking of it as bits. And XORs, they work like adding modulo 2. So this is how the one-time pad scheme works. The way you encrypt the message with a key K is you just XOR it with the key. And the way that you decrypt is also very simple. What you get, you just XOR it with the key again, because when you XOR a key with itself, it cancels out, so you end up with the decryption. Now, we saw that the one-time pad gave perfect secrecy. And what did that mean? That means that seeing the ciphertext does not change Eve's probability distribution for the message. So the probability of any particular message, given that you observe a ciphertext, is the same as when you don't observe the ciphertext. So the ciphertext and the message are independent. So from a theoretical point of view, this is as secure as encryption can be. This is perfect secrecy. But the one-time pad has very strict requirements, right? So we saw the key must be truly random. It must be the same length as the message, and it must never be reused, right? And so the last part is especially important. If the same key is reused, the system can leak information. And so the main issue with this one-time pad, so you can use one-time pad, but what is the main issue with it is one of practicality. So for a long message, we need an equally long secret key. And for many messages, we may need many long independent keys. And sometimes this is not the most realistic, right? Also, the issue of how you transmit the keys, which is what we're going to get to in this lecture. How do you send keys themselves? Because, of course, once the keys are known here, you can do this scheme, but how how does Bob get this key, right? And there are settings where they could meet ahead of time and so on, but we're going to see also the interesting problem of actually transmitting the key through the channel, right? So what happens with many modern cryptographic schemes is that they do not look at perfect secrecy. They look at something which is called computational security. And so the ciphertext may contain information in principle, but no efficient attacker should be able to extract useful information from it. So that's going to be a trade-off that we'll be doing later on. I'll mention that one of the major tools in modern symmetric key cryptography is something called a block cipher. And so a block cipher is a deterministic encryption algorithm that acts on fixed size blocks. And so for a fixed size key K, the encryption takes something of size n and gives something out of size n. And the idea here is that this key can be much smaller than the message. And of course, because of that, you're not going to get perfect security. You will get computational security. But I mean, if one is able, and there's a whole field of studying computational security and things like that, and we'll talk about some of that stuff, right? And so, like we saw before, with the one-time pad, security is unconditional, but the key must be as long as the message. With block ciphers, security is computational, and so we assume that without the key, no efficient attacker can distinguish between the encrypted data and maybe something looking random, right? And a standard example, and the most popular one, is known as AES, which stands for Advanced Encryption Standard, right? There were older examples that were broken. You know, you have other stuff and many more than what I'm showing here, of course. But this is the current standard that is used.